Middle East Technical University, Ankara, Turkey. My name is Akif. I am this year's team leader, and today me and my teammates are gonna proudly present our new rover Bitanit. As captain, my function is to oversee project management and system integration across these disciplines. We are participating in the European Rover Challenge because we want to experience the scale and energy of a major international competition. We established our commitment early on by winning the Jury Special Award in our first European Rover Challenge. Since then, we placed 7th in the Anatolian Rover Challenge 2022, competed as a finalist in the European Rover Challenge 2024, and most recently achieved 5th place at the Anatolian Rover Challenge 2025.
Our responsibility as a mechanical team is to build the physical core of the rover. We engineered the structural stability, the drive systems, and the robotics that needed to overcome challenges on the field. This year, we built upon the experience and the architecture of our previous designs. We focused on continuous improvement, carefully optimizing everything from the mainframe down to the smallest parts, to meet the strict competition standards. To show you where it all begins, we will start with the chassis design.
In our chassis, we are using aluminum sigma profiles due to ease of assembly and modularity, while integrating CNC and 3D printed lightweighted parts. Also for the suspension, we are using a rocker bar mechanism located under our chassis that ensures all wheels are remaining in continuous contact with the ground, allowing us to safely traverse rocks and climb slopes up to 40 degrees without losing stability. With a footprint of 120 cm in length and 70 cm in width, the rover maintains a substantial 43 cm of ground clearance.
Moving on to mobility, four-wheel drive and four-wheel steering architecture enables a fully independent drive and high maneuverability by using brushed DC motors paired with high-torque gearboxes. This system enables advanced mobility capabilities including zero-radius turn and crab walking. To safeguard our powertrain, the brushed DC drive motors are housed with rugged aluminum hubs and custom PETG coverings to shield them from dust and external impacts. For optimal surface contact, the wheels are 3D printed from flexible TPU and featuring a custom engineered grosser geometry that maximizes mechanical grip on loose soil.
Our robotic arm features 5 degrees of freedom, designed to handle complex challenges of ERC tasks. The primary lift axis uses a powerful linear actuator that delivers 1000 newtons of force. This provides smooth movement and gives the arm 5 kg payload capacity. Importantly, the actuator locks in place during the power cuts, preventing any uncontrolled movement of arm.
For the second joint, we designed a custom polarity gearbox paired with a brushless DC motor, outputting an impressive 80 Nm of torque. The third joint is driven by standalone brushless DC motor providing 80 Nm of torque. Additionally, we integrated a precise worm gearbox at the base axis. This setup provides an automatic self-locking system that holds the arm position during power cuts.
Right after these stages, we implemented a differential bevel gear assembly leading to the end effector. This compact mechanism features very low backlash and provides the wrist agility needed to approach objects from any orientation or angle. To balance strength and weight, we combined high-strength carbon fiber tubes with laser-cut 6061, T651 aluminum plates and PETG parts. This hybrid structure makes the arm lightweight, durable, and modular. The arm has a wide operating range, boosting a 1.5 meter reach, an elevation from positive 80 to negative 24, and a full 360 rotation at the base. Equipped with custom interchangeable grippers, this system guarantees the precision needed for both maintenance and sampling operations.
We designed and built a lightweight drone. The custom carbon fiber frame was manufactured entirely by our team. To ensure maximum durability with minimal weight, the structure was fully optimized using stress analysis in CAD before production.
For flight control, a Kakuta F722 ensures mid-air stability and relays critical real-time telemetry back to our operators. Safety is paramount. The operator can take manual control or trigger an emergency autolan instantly. Hard-coded fail-safes also automatically execute a safe descent if telemetry is lost or battery drops. For autonomous droning subtasks, a Raspberry Pi 02W runs for image processing and decision-making logic, which was built exclusively in MATLAB and Simulink. This natively running code enables the drone to map probes, identify targets, and execute a fully autonomous precision landing on our custom rover platform.
As the electronics team, we are responsible for developing the rover's electrical and communication framework. We ensure reliable subsystem integration throughout stable power distribution and efficient method transmission. This enables consistent and reliable rover performance throughout mission operations. Our rover uses two communication systems to ensure reliability during mission. The main communication system is responsible for transmitting high-bandwidth data such as video and photogrammetric information. For this purpose, we use devices operating at 5 GHz with an omnidirectional antenna to provide stable communication. In addition, we implemented a backup communication system based on LoRa technology. This system operates at 868 MHz and is used for automated data transmission and error checking. Using both systems provides redundancy and allows the rover to maintain communication, even if the primary link experiences problems.
At first, we built and tested our circuits on these perf boards. This helped us quickly check the basic functions and understand if the system were working properly. After the testing phase, we designed our own custom PCBs to create a more reliable and organized electronic system for the rover. Here you can see some of the electronic systems we developed for the rover. One of these PCB designs is a drive board that will work together with the RoboClaw motor controller to control two motors at the same time. We also designed two additional PCBs for the robotic arm system. These boards are planned to drive a total of 7 motors. Although the PCBs are still in production, this design process helped us improve the overall structure and integration of the rover's electronics.
To ensure maximum electrical stability and safety, our rover utilizes an isolated dual battery system. We separate power into main battery for hydro components and motors, and logic battery for communication systems, sensitive sensors, and computers. This system protects our sensitive electronics from multi-induced electromagnetic interference and voltage drops. For multi-layered safety, our power line has an emergency stop button connected to central relays for instant shutdown. Also, reusable main fuses for main and logic battery backed by individual fuses for every single PCB.
Hey, I'm Eyman from Metu Rover software team. As the software team, we built a highly decentralized architecture to maximize reliability. We push vision processing to edge to optimize our autonomous navigation. Meanwhile, dedicated microcontrollers handle precise motor control, and everything is monitored through one centralized dashboard. Our vision pipeline uses 4 Raspberry Pi Zero 2 volts for a 360-degree view. By migrating to hardware-accelerated WebRTC and offloading encoding via the deep camera stack, we keep bandwidth around 20 megabits per second to prevent network bottlenecks. Crucially, this edge computing approach frees up our Jetson Orin NX to exclusively handle our computationally heavy autonomous navigation stack. Built on ROS2 Humble, it utilizes Nav2 for dynamic path planning and RTAP map for SLAM, processing depth and visual odometry directly from our Z2 stereo camera. For precise motor control, custom PID controllers on Raspberry Pi Picos continuously route encoder feedback over both CAN bus and Ethernet networks. Finally, we manage it all through a centralized command hub using NASA's OpenMCT framework, translating complex telemetry into a dynamic dashboard for rapid decision making.
Hello, I'm Esma Nursuman. I'm Metu Rover Science Team Captain. As Metu Rover Science Team, we conduct a literature review to understand the geological background. Following the research, we use JMARS, QuickMap, and USGS databases for understand the geological and mineralogical information about the given region using orbital data. Throughout this process, we continue reading scientific sources. This year, for our field operations, we have developed 4 distinct experiments for this period. Hydrochloric acid for carbonate detection, hydrogen peroxide for oxidation potential, burette for protein identification, and Lugos test for organic complexes.
Finally, we take the data obtained from these 4 wet chemistry experiments and integrate it with our live gas sensor data. By combining the soil analysis and atmospheric readings, we compile a verified, single data profile of the area.
Our science sampling system is driven by 2 DC motors. The first motor provides smooth linear activation to lower the mechanism, while second motor powers our 3D printed drill. To maintain stability during drilling, we also integrated a custom vibration reducer into the assembly. The drill is engineered to reach depths up to 30 cm in the soil. Once extracted, the soil is transferred into our specially designed onboard sampling module. This module contains 6 individual tubes, each capable of holding 25 grams of soil, giving us total maximum capacity of 150 grams. To guarantee compliance with the competition's 100 gram minimum requirement, we integrated a weight sensor into the sampling cup. This allows the system to measure the sample's weight continuously during the loading process.